For nearly a century, we've called it dark matter because it doesn't emit, absorb, or reflect light. It's invisible to every telescope ever built, detectable only through its gravitational effects on visible matter. We've measured its presence in galaxy rotation curves, gravitational lensing patterns, and the cosmic microwave background. It comprises approximately 85% of all matter in the universe, yet we've never directly observed a single particle of it. The name dark matter reflects this fundamental property. It's matter that's dark. Except new observations from multiple independent research teams suggest we've been fundamentally wrong about this defining characteristic. Dark matter isn't dark. It interacts with itself through forces we didn't know existed, creating dynamics we never predicted. And this revelation doesn't just change our understanding of dark matter. It changes everything about how the universe evolved, how galaxies formed, and potentially what dark matter actually is. The first hints emerged from observations of galaxy cluster collisions. When two massive galaxy clusters merge, the collision happens in slow motion over millions of years. Galaxies themselves, being mostly empty space, pass through each other largely undisturbed. But the hot gas between galaxies collides and interacts, creating shock waves and heating that we can detect through X-ray observations. Dark matter, according to standard models, should pass through everything including itself without interaction, like galaxies do. Its only significant interaction should be gravitational, but detailed observations of multiple collision events show something different. The dark matter doesn't always move with the galaxies. In some collisions, it lags behind, creating separation between where the dark matter is concentrated and where the visible galaxies are located. The most famous example is the Bullet Cluster, two galaxy clusters that collided approximately 150 million years ago. Observations show the hot gas concentrated in the collision zone between the clusters, slowed by interactions during the merger. The galaxies pass through and are now separated from the gas. Gravitational lensing measurements reveal where the mass is concentrated, and therefore where dark matter must be. In the Bullet Cluster, dark matter appears concentrated with the galaxies, separated from the gas, exactly as standard cold dark matter models predict. This observation was celebrated as proof that dark matter exists and behaves as expected, interacting only gravitationally. But subsequent observations of other cluster collisions revealed cases that don't fit this pattern. The galaxy cluster Abell 3827 shows dark matter distributions that can't be explained by purely gravitational interactions. The dark matter appears offset from the galaxies in ways that suggest self-interaction. Dark matter particles colliding with other dark matter particles and transferring momentum. The cluster system, MACS J0416, shows similar offsets. And detailed reanalysis of older collision observations, applying improved measurement techniques, reveals subtle offsets that weren't apparent in initial studies. The pattern suggests dark matter does interact with itself, not through electromagnetism or any force we're familiar with, but through a previously unknown force that operates specifically between dark matter particles. Before we examine what these interactions mean for the universe's structure and evolution, make sure you're subscribed to Cosmic Outliers and hit that notification bell. This is one of the most significant developments in cosmology in decades, and new observations keep arriving. Drop a comment with what you think dark matter actually is, because the evidence is forcing cosmologists to reconsider fundamental assumptions. The theoretical framework for dark matter has evolved over decades. Early proposals in the 1930s suggested missing mass to explain galaxy cluster dynamics. By the 1970s, galaxy rotation curve observations by Vera Rubin and others demonstrated that galaxies contain far more mass than visible matter accounts for. This invisible mass became known as dark matter. The leading hypothesis proposed weakly interacting massive particles, or WIMPs, particles that interact only through gravity and the weak nuclear force. WIMPs would be produced in the early universe through known physics and would have the right properties to explain observations. Crucially, WIMPs shouldn't interact with each other significantly except gravitationally. They should be collisionless, passing through themselves and ordinary matter alike without meaningful interaction except through gravity's influence. This collisionless assumption became a cornerstone of cosmological simulations. Computer models of galaxy and structure formation assume dark matter particles move through space influenced only by gravity. These simulations reproduce many large-scale features of the universe: the cosmic web of filaments and voids, the distribution of galaxy clusters, the properties of the cosmic microwave background. The success of these simulations was taken as confirmation that dark matter is indeed collisionless, but there was always a problem at small scales. Simulations predict more small satellite galaxies around large galaxies than we observe. They predict dark matter density profiles in galaxy centers that don't match observations. These discrepancies, known as the missing satellites problem and the core-cusp problem, have puzzled cosmologists for years. Self-interacting dark matter with additional non-gravitational forces between particles, could solve these small-scale problems. If dark matter particles can collide and exchange momentum, energy, and possibly other properties, the dynamics change. Self-interactions would tend to smooth out dark matter distributions, creating cores rather than cusps in galaxy centers. They could suppress the formation of very small dark matter halos, reducing the number of tiny satellite galaxies. Simulations incorporating self-interacting dark matter reproduce observations better than collisionless models, but only if the interaction strength is precisely tuned. Too much interaction in large-scale structure doesn't form correctly. Too little and the small-scale problems persist. The required interaction strength falls in a narrow range that seemed suspiciously fine-tuned. Now observations are independently suggesting that dark matter does self-interact, and with cross-sections close to what's needed to solve the small-scale problems. This is remarkable. The observations don't come from fitting models to galaxy structures. They come from direct measurement of dark matter distributions in colliding clusters. The fact that the inferred interaction strengths match what's needed to solve independent problems suggests we're not seeing noise or systematics. We're seeing a real physical property of dark matter that's been there all along, but only now becoming measurable with sufficient precision. What does it mean for dark matter to self-interact? It means there's a force operating between dark matter particles. Not gravity, which we already account for. Not electromagnetism, which dark matter definitively doesn't experience. A new force, or at least a force we haven't detected before, that couples to dark matter particles. This force would need to have specific properties. It must be strong enough to cause measurable effects in galaxy cluster collisions, but weak enough not to disrupt large-scale structure formation. It probably has short range, operating only when dark matter particles pass very close to each other, and it must couple only to dark matter, not to ordinary matter, or we would have detected it in laboratory experiments. The possibility of a dark force, a fifth fundamental force that only dark matter experiences, has profound implications. It means the dark sector, the collection of dark matter particles and whatever interactions govern them, is more complex than we assumed. Perhaps dark matter isn't a single particle type, but a family of particles with rich interactions among themselves, a dark periodic table of elements that exist in parallel to the ordinary matter periodic table we know. Perhaps there are dark photons mediating electromagnetic-like forces between dark-charged particles. Perhaps there are dark atoms, bound states of dark protons and dark electrons held together by dark electromagnetism. This might sound like science fiction, but it's serious theoretical work being pursued by particle physicists trying to understand what the observations are telling us. If dark matter has complex self-interactions, it could radiate dark photons, losing energy in processes analogous to how ordinary matter radiates electromagnetic photons. This would make dark matter cool, in the thermodynamic sense, allowing it to dissipate energy and collapse into more compact configurations than collisionless dark matter could achieve. This cooling could explain structures we observe but don't fully understand, like the ultra-compact dark matter cores some galaxies appear to have, or the peculiar distributions of dark matter in certain dwarf galaxies. Cooling dark matter could even form dark matter disks within galaxies, concentrated structures of dark matter that mirror the visible galactic disks of stars and gas. The observations forcing this reconsideration come from multiple independent sources. Galaxy cluster collision studies are one line of evidence. Another comes from detailed modeling of galaxy rotation curves. Precision measurements of how rotation speeds vary with distance from galaxy centers show features that pure gravitational models struggle to explain. Adding self-interacting dark matter improves fit significantly. Yet another line comes from gravitational lensing studies. The way background galaxy images are distorted by foreground dark matter distributions reveals information about dark matter's spatial structure. Some lensing observations show features consistent with self-interacting dark matter but hard to explain with collisionless models. Perhaps most intriguingly, observations of dark matter distributions in the centers of galaxies show diversity that collisionless models don't predict. Some galaxies have cuspy dark matter profiles, density increasing steeply toward the center as collisionless simulations predict. Others have cores, central regions where dark matter density flattens. The distribution of cuspy versus core galaxies correlates with galaxy properties in ways suggesting that self-interactions, modulated by galaxy evolution and star formation history, create the diversity. Collisionless dark matter should produce similar profiles in all galaxies of similar mass. Self-interacting dark matter, with interaction rates depending on dark matter density and velocity, naturally produces variation. Direct detection experiments searching for dark matter have yet to find definitive signals. These experiments look for dark matter particles from the galactic halo passing through detectors on Earth and occasionally interacting with atomic nuclei. Decades of increasingly sensitive searches have produced null results for WIMP-like particles in the expected mass ranges. This null result, combined with null results from particle collider searches for WIMP production, has pushed the WIMP hypothesis into increasingly constrained parameter space. Self-interacting dark matter doesn't necessarily help with direct detection. If dark interactions are mediated by new forces, those forces don't need to couple to ordinary matter at all. Dark matter could interact strongly with itself while remaining completely invisible to direct detection experiments. This makes the problem harder because we can't test dark sector physics in laboratories. We're dependent on astrophysical observations to reveal dark matter's properties. Theoretical models of self-interacting dark matter explore various possibilities. The simplest involves dark matter particles interacting through exchange of force-carrying particles, analogous to photons in electromagnetism. The interaction strength is characterized by a cross-section, essentially the effective size of dark matter particles for collision purposes. Observations suggest cross-sections around 1 square centimeter per gram of dark matter mass work well. This is tiny by everyday standards but significant on particle physics scales. More complex models involve multiple dark matter particle types interacting through multiple dark forces, creating rich phenomenology. Some models include dark matter particles that can form bound states, dark atoms or dark molecules that would have entirely different behavior than free dark matter particles. The implications for galaxy formation are profound. In the standard picture, dark matter collapses first into halos, gravitational wells, where ordinary matter then falls, and forms stars and galaxies. This process is driven entirely by gravity. With self-interacting dark matter, the collapse dynamics change. Dark matter can lose energy through dark interactions, potentially collapsing faster or into different configurations than collisionless dark matter. The feedback becomes bidirectional. Star formation and supernovae explosions in galaxies create outflows of ordinary matter that push on dark matter gravitationally. If dark matter can respond by thermalizing and redistributing, the coupled evolution of dark and ordinary matter becomes more complex and potentially more realistic than models assuming collisionless dark matter. Early universe cosmology also changes. In the first fraction of a second after the Big Bang, dark matter was produced through processes we don't fully understand. If dark matter has self-interactions, the production mechanisms could be different than WIMP production models assume. Dark matter might have been in thermal equilibrium with itself through dark forces, even if it wasn't in equilibrium with ordinary matter. This would affect predictions for dark matter particle masses, abundances, and velocity distributions. Subtle features in the cosmic microwave background radiation and large-scale structure could carry signatures of these early universe dark interactions. Current observations don't require changes to early universe models, but future precision measurements might reveal discrepancies that self-interacting dark matter could explain. The transition from thinking of dark matter as boring, collisionless stuff that only gravitates to thinking of it as dynamically interesting material with its own complex physics represents a paradigm shift. For decades, dark matter was treated as gravitational scaffolding, important for structure formation but otherwise passive and uninteresting. Attention focused on ordinary matter, the stuff that forms stars, planets, and us. Now we're realizing that the dark sector might be just as complex and interesting as the visible sector, with its own forces, possibly its own periodic table of particles, and dynamics we're only beginning to understand. This is both humbling and exciting. Humbling because 85% of the matter in the universe is stuff we don't understand at a fundamental level. Exciting because we're potentially on the verge of discovering an entire hidden layer of physics. The practical implications for astronomy are significant. If dark matter self-interacts, we need to revise galaxy formation models, structure formation simulations, and predictions for dark matter distributions in various environments. This affects interpretation of gravitational lensing data, predictions for satellite galaxy populations, understanding of galaxy evolution, and searches for dark matter annihilation or decay signals. It also opens new observational avenues. If dark matter can cool and form compact structures, we might be able to detect those structures through gravitational effects even if they contain no ordinary matter. Dark matter-dominated dwarf galaxies, objects with little or no stars but significant dark matter, could exist and be discoverable through sensitive surveys. The terminology dark matter might persist for historical reasons, but it's increasingly misleading if dark matter interacts with itself through non-gravitational forces. The interactions might not produce visible light, keeping dark matter dark in the electromagnetic sense, but they make dark matter dynamically bright, radiating energy and momentum through whatever dark forces operate. Perhaps we should think of it as interacting matter that happens to be invisible rather than dark, non-interacting matter. The shift is subtle but conceptually important. It changes dark matter from a passive gravitational backdrop to an active dynamical player in cosmic evolution. The observational evidence continues accumulating. Every new galaxy cluster collision studied with modern instruments provides data on dark matter behavior. Statistical analyses combining many observations are reaching the precision needed to distinguish between collisionless and self-interacting scenarios. The next generation of observatories, including improved X-ray telescopes for studying cluster gas, gravitational wave detectors that might observe dark matter-related phenomena, and optical surveys mapping billions of galaxies for lensing studies, will provide unprecedented constraints on dark matter properties. Within the next decade, we should know definitively whether self-interactions are real and be able to measure their strength with percent-level precision. Meanwhile, theorists are exploring what particle physics models could produce the required self-interactions. This is challenging because the models need to explain why dark matter interacts with itself, but not with ordinary matter, why the interaction strength has the specific value observations suggest, and why direct detection experiments haven't seen anything. Various solutions have been proposed involving hidden sector particles, gauge symmetries that only dark matter respects, and specific mass ranges and force carrier properties that evade current experimental constraints. Some models make testable predictions for future collider experiments or rare decay processes that next-generation detectors might observe. The interplay between astrophysical observations and particle physics theory is driving progress on both fronts. The philosophical implications are worth considering. We named dark matter dark because we couldn't see it. We assumed it was simple because we had no evidence for complexity. Now evidence suggests it's not simple, and the label dark might be misleading. This is a reminder that absence of evidence isn't evidence of absence. Just because we haven't detected dark photons or dark forces doesn't mean they don't exist. They might be abundant and important, but simply don't interact with our detectors. The universe could be filled with phenomena we're blind to, not because they're intrinsically invisible, but because we don't have the right instruments or understanding to detect them. Dark matter might be the first example of a broader phenomenon, hidden sectors of physics operating according to their own rules that only become apparent through indirect effects. We're living through a transition in our understanding of what comprises the universe. A century ago, we thought everything was ordinary matter governed by gravity and electromagnetism. Now we know ordinary matter is the minority. Dark matter dominates. Dark energy drives cosmic acceleration, and the dark matter might have its own complex physics. We're only beginning to glimpse. Each revelation makes the universe stranger and more interesting. Each answer raises new questions. If dark matter self-interacts, what are the force carriers? What symmetries govern dark sector physics? Are there dark analogs of nuclear forces? Could there be dark life? Structures of dark matter complex enough to process information and evolve? These questions sound speculative, but they're logical extensions of taking self-interacting dark matter seriously. The practical question is how to test these ideas. Astrophysical observations will continue providing constraints, but they're indirect. We need ways to probe dark matter properties more directly. Proposals include building more sensitive gravitational wave detectors that could observe dark matter-related phenomena, conducting larger direct detection experiments optimized for different mass ranges and interaction types, and designing collider experiments specifically targeting dark sector particles. Each approach has challenges and may require decades of development. But the potential payoff is understanding what most of the universe is made of, surely one of the most fundamental questions in science. As we learn more, the picture will likely become more complicated before it becomes clearer. That's how science works. Simple models are replaced by more complex, but more accurate models, which eventually get refined into new simple models that capture the essential physics. We're in the complicated middle phase for dark matter. The simple WIMP model didn't work. We're exploring alternatives involving self-interactions, hidden sectors, and new forces. Eventually, a framework will emerge that explains all observations consistently. That framework might look nothing like what we imagine now, or it might vindicate ideas already proposed but not yet tested definitively. Either way, the journey of discovery is revealing a universe far richer and stranger than we imagined. If this exploration of how dark matter might not be dark after all changed your perspective on what fills the universe, hit that like button and subscribe to Cosmic Outliers for more investigations into the hidden layers of reality we're discovering. Drop a comment with your theory about what dark matter really is and whether you think there's an entire dark sector of physics parallel to ordinary physics. The evidence is mounting that we've been missing something fundamental, and understanding it will rewrite cosmology from the ground up.